Okay, okay, guys. Let's go over the routing real quick. The routing real quick. Um, this is one of the most fundamental part of data communication and networks. So it's very, very important that you at least understand how routing is done on most networks and the various types and algorithms, protocols that goes with it as well. This slide should be on the course page, and I think it's under week 8, under lecture 10, if I'm not mistaken. So you can just download it and we can just go through it. So anyways, routing generally covers mostly the network layer of the OSI model, and they more focus on delivering and forwarding of packets. So we want to look at how devices like routers or at the layer 3 level, how information is moved from one source to a destination. So some of the various functions that the network layer plays, it's revolves around transport of packets from a sending node to receiving node, obviously. So if you're within a given network and you want to send a packet across, it's the job of the network layer to figure out which route to move the packets from your device to wherever you just want to send a message to, across the internet or either across a small network or a wider network, which includes the internet. And to go through that process, there are a number of things that must go on, obviously. So you do have elements like protocols, very key to how the network layer handles the packet formations and packet transportation as well. Because we don't want a situation where you have a number of devices send information across, but it can't get through. So it's the job of the network layer protocols to make sure some of these challenges that comes with congestions, traffic delays, and what have you are well streamlined, so at least messages don't get lost in translation or in transit on their way to their destinations. So the some devices that involves are mostly host devices and then the routers. Yeah, so like your PCs, your cell phones, going to a router, multiple routers across the networks to make it possible for that information to go through back and forth. So you do have how the network layer plays a key role in handling most of these. So you can tell that from the OSI model, when a message goes across, it has to go through physical all the way up to the network layer at every given junction within the network when it comes to routing the packets all the way till it gets to the final destination. So we hit more or less the third layer of the OSI model a lot within routing. That's where most of the key functionalities and overlays of how information is smoothly carried across are well uh, looked at within routing. Uh, Three important functions that you want to really keep in mind, or that makes the network layer very efficient in its transmission of information, is path determination, because you want to make sure you have the right path in terms of especially if you're within a network of various or multiple network devices, you want to understand, the various path that you have, because if you have, let's say, 1,000 nodes or routers that you have to route your packets through to get to a final destination, you really have to understand, and how that node, that path are determined, and how to get from one node to another within that, cluster of meshed topology that you might have to transmit information through. And you also know how to figure how to switch. You also need to know how to switch the messages, because when information comes through, they come on various ports and various transmission mediums, or from various telecommunication networks. So it's very important that the network layer try to figure out how to switch those information as well. So at least when it's moving them across, it can help move the packets from the router's input to appropriate output of various routers that needs information to carry on to their final destination. And then finally, you have uh, the call setup, which is quite optional, but definitely very important, especially when it comes to routing VoIP services over the internet. You need to understand how call setups are done. When you adopting the virtual circuit packet switching within the layer 3 or within uh, packet switching networks, you need to understand how the call setup is going to be done for that VoIP services to move on, so to take effect in transmitting that call within a network. So some network architecture require routers to make calls along path before data flows. And even when it comes to ATMs, for instance, which is a packet switching network, it requires dedicated path to be implemented, to be set up before information cells can be moved across the ATM networks. So some of these are very important uh, uh, when it comes to layer 3 functionalities within routing. Models that I use to handle the network services, um, quality, or how you can guarantee bandwidth. Bandwidths are very important. If you don't have enough bandwidth within a transmission, within a given network that you have, you could have a lot of challenges moving your packets, or it creates a number of challenges for layer 3 to function efficiently. So guaranteeing of bandwidth is very essential. Um, and you also have to look at preservation of interpackets timings to avoid jitters. So at least informations don't get buffered or slowed down, or don't literally just stall in transmission. And then you also have to look at just a model. You just have to look at loss-free deliveries. If you transmit a really essential message, you want to make sure that at least you guarantee that the message is transmitted without any losses, any packet drops, or uh, uh, missing packets in transmissions. You want to make sure some of these things are well sorted out, and it's part of the key models that Netically adapts as well to address routing needs within a given network, and also in terms of delivery order, because messages since are broken down in packets and a network and a packet switching. So packets are broken. So information are broken down in packets, and packets switching networks. You have to look at the order through which the message are delivered, because if messages go through various routes as packets on route to a very particular destination, it's very important that when it hits the final destination, the right order is in place, or right measures or models are put in place to put back the packets in their right orders before actually delivering it to the receiving node. We don't want a situation where you send a high message and then H got there to the receiving end first, and I then becomes IH instead of HI. We don't want to treat it like that. So obviously, the order delivery is quite essential to network services in terms of moving packets across the network. And then you also look at congestion and feedbacks from senders and even to senders. So at least if there are issues within a network, it's important that that information is communicated back and forth. between the various nodes. So at least at any given point in time, there is that knowledge or that status update of a given network that the packet has been moved across. Another model used in looking at some of these network services is within your datagram networks. Now, keep in mind, datagram is very important for what? Moving packets that have got variable bits transmissions. Virtual circuits are more for the what? The constant bit streams, where you don't want breakages like VoIP services. You don't want breakages in them. So at least when you have a dedicated path, those packets that have been transferred will take that path and route to their destination. But when it comes to datagram, it doesn't really matter. We don't need a dedicated path for that. You just need a message to move across the network reliably through the most reliable and effective um, route or path, and with the most least cost to get a message to its final destination. So when it comes to datagram networks, which like I said revolves around moving packets that are more or less in variable constant bit streams, you need to know how calls are set up. No, sorry, you don't need to know how calls are set up because these are more variable packet information that have been streamed across the network or that have been moved or forwarded back across the network. And definitely there's no need a call setup. Like the internet, a typical example of moving packets, data packets like your WhatsApp messages or browsing or um, accessing resources from the internet, downloading movies or files or whatever. Those don't necessarily require a call setup like the way you would for a virtual circuit transmission, which will be for the VoIP services. So call setups are not required when it comes to datagram transmissions, and one of the internet models for the network layer. Routers that need not know the state about end-to-end connections, and no network layer concepts of connections are required, which means connection orientations are not very important when it comes to datagram networks. There's a lot of discussion about how uh, unsecure datagram is as compared to uh, TCP, which is very essential when it comes to the security levels. We'll talk about that during TCP/IP vulnerabilities. But Datagram is not much quite reliable in terms of these models that it has. Like I said, you don't need a call setup. The router does not need a state about end-to-end connection. So even if there are problems going on within the networks, it's not up to the job of the router to really understand or know it very well. It depends on the transmission, but generally not really necessary. Just to keep things within reasonable transmissions, routers do not need a state of various end devices. But we'll look at other algorithms and protocols that require some of these things. But generally, Datagram does not uh, require some of these end-to-end status to be established before transmissions take place. So in generality, most people say Datagram is not the most reliable in terms of security and efficiency when it comes to moving packets across the network or routing. It's not quite reliable. TCP/IP is much more reliable because you do have the handshake, uh, the uh, the three-way handshakes to make sure transmission is well determined and well organized before transmission takes place. So at least when the transmission is ongoing, it has that reliability within uh, the transmission medium across the networks. And packets typically routed using destination host IDs only. The packets between same source destination pairs may take different paths. Not really care so much about whether they get to the destinations or not. But it's very important to have that in mind that you need to know some of these key informations. Generally, though, like I said, packet datagram networks does not require that call setups, and also packets are moved between source and destination in various paths. It's very essential. We don't really need to have that essential guaranteed in terms of where the packets are at a given point in time, or you just want to access a particular information without a need to know everything about the topology of the network that's the message needs to pass through, then it's quite essential that Datagram plays a key role in helping us move packets back and forth within the network. With that said, though, Datagram is very essential to how uh, information, especially data-wise, are moved across the internet. They play a key role. As a matter of fact, um, most transmissions use datagram a lot. So it's one of the biggest a network being used to move packets across the internet a lot. We'll look at other levels of it that really allows you to establish better transmission need to guarantee the information is being transmitted, especially when it comes to the routings, algorithms, and various protocols that have been put in place to make sure, even though um, packets are moved through various paths and call setup are not required, or there's not really a requirement to have a state a condition of all end-to-end connection within a given network, but it's still important to make sure that information you transmit have got that uh, reliability to it. So we'll look at some of those within the routing algorithms and protocols that comes up later on. So let's look at how a datagram works within a given illustration. Here you'd have a network of about here we have about 6 routers or 6 nodes that are moving packets across them. In this scenario, PC1 is trying to send a message to PC2 or host 2 over here, which is on this side of the router or on this side of the network. And the network it's well interconnected. So it's the job of um, the nodes within a network to find the most effective and reliable path or ways to determine the correct path to move the packet across this network, so at least the message being forwarded to um, PC2 can be transmitted to it or can be received reliably and on time and effectively as well. So we do have 2 packets coming across, and in this scenario, we have when the 2 packets came in, they got stored. The router determines the appropriate path to forward the message across, and since this happens to be a datagram network, there's no need to worry about the current status of the entire network within this setup over here, especially when you're looking at uh, uh, the distance vector routing. You do not need to know the current state of all the neighbors across the entire network topology you have. So in this scenario over here, you have 2 packets coming through, and the packets are being routed through different paths on its way to the final destination. So it's the job of the routers to figure out which path is much more appropriate or reliable to forward the packets through. And so in this case, there's no need to forward all packets through one path. It's ideal to use various paths, especially when you're talking about datagram networks. You can use multiple paths to forward the packets across. And at the end of the day, when it gets to the final node that's supposed to hand the message to PC2, it would know how to basically group the message back together or rearrange the message back together before handing over to uh, PC2 in the right format and in the right order as well. But within the transmission, that those packets might have gone through a number of various different paths. So in order to make sure the information being transmitted, like I said, follow a good delivered reliably and efficiently as well as effectively, we put protocols in place. Even though we're using even though we're within a datagram network, we try to look at how protocols play a key role in making sure that regardless of whether we're within a datagram network or a TCP/IP network transmission, we can still guarantee that the message we transmit goes to their respective receiving nodes in the right order, in the right format, without any issues or errors or what have you. Okay, so that's where routing protocols uh, come into play or play a key role in addressing some of these issues. So the goal of routing protocol is to determine a good path, which is the sequence of routes that needs to be that needs that the packets needs to go through in order to get to the final destination through the network is what we term a good path. So it's the goal of routing protocol to determine the good path or the sequence of routers or routes through a given network from source to destination for a given message being transmitted. So within that, it's very important to have a layout of how the network is structured. So at least when you uh, employ a given routing protocol, you guarantee that a message you're transmitting can be securely transmitted across the internet or the networks to the final destination. So good path typically just means minimum cost path, other than other default possible path that you might have. So graph abstractions for routing algorithms are very essential, which means we need to know the graph nodes or the routers within the networks. We also have to have graph edge concept within the various physical links, especially when it comes to the cost, so we can identify delays and congestion level within the networks. And it's a job of routing protocols to look at some of these things through routing algorithms to help us move packets back and forth efficiently. So generally, when you're looking at routing protocols, you need algorithms that can help make sure that the message that you transmit uh, um, are moved across the network um, effectively using the least cost with no delays and going through the minimum possible path to deliver the message. And one thing you need to keep in mind is that the job of a router or the essence of routing is just to make sure that we store message, so we store and forward message reliably across a given network. Okay? And at the most fastest possible time. Nobody wants a router or a routing uh, transmission means or medium where there's so much delays on it. Nobody wants that. So it's a job when routers were built or routing protocols were put in place. It was to address key issues whether it relates to time to deliver a particular message across a given network. That's why minimum costs are very, very essential to routing. So now let's look at some of the algorithms that are used to help move packets across efficiently across a given network. In terms of classifications, routing algorithms, I've got a number of classifications. Let's go through them real quick. We do have static. Um, we do have, we have the global and decentralized classification for routing packets. When it comes to global, we're looking at how uh, messages or routers move packets across a given network, looking at the link state of that particular network topology that the router finds itself in. So in terms of globalizations, link states are very important in the algorithms of routings classifications. So generally, all routers must have complete topology, link cost information uh, of a given uh, network to help move packets across it much more efficiently. So that's what we talk about link states allowed within the globalizations classification. And a decentralized classification, routers only knows physical connected neighbors. So link costs to neighbors only are essentials. And we have iterative process of computing and exchanging information across the various neighbors. So at least we can discover our neighbors and their status in terms of their link cost. So when it comes to moving packets or when the packet gets up at a given router, it will know how to forward that message to its to a given neighboring router to forward the packet en route to its final destination. So this is where distant vector algorithms play a key role in helping us address uh, how packets are moved across an interconnected network. Let me go back to a global, which essentially revolves around the link state, where every router needs to know a complete topology uh, status or state for a given network that it finds itself in. Link states uh, are very essential to intra-domain network connections. So this is where we look at routing protocols like RIB or Open Shortest Path Possible or OSPF. So if you're in the network environment, if you're a network administrator or you're already at in a network environment at your workplace or whatever, you will notice some of these things play a key role. Some of those two protocols play a key role in how your organization move packets across the given respective networks, either to their branch offices or um, their satellite uh, campuses or some of their uh, let me use customers or what have you. You notice that RIB, OSPF, those two link state routing algorithm plays a key role within those organizations. Decentralized, on the other hand, which is just distant vector algorithms, would fall more or less on the uh, interdomain. Sorry. Okay, I think I messed up on one of the. Let me just reiterate the global in terms of the link state algorithm. I did point out the RIP and an OSPF. Technically, RIP falls under a distant vector routing. Sorry about that. Because it uses various vectors to determine how routes are forwarded across its neighbors. So it's not so much as uh, interested in how an entire topology is set up. So generally, within a link state, Uh, OSPF